Okay, so a polynomial function, there in the first thing, the polynomial function can be written in the form, and you just see a bunch of letters, a sub n, x to the n power, a sub n minus 1, x to the n minus 1 power, so on and so forth. And so you've seen polynomial functions, typically we've been focusing on that, right? X squared, x, and then no x. That's the quadratic piece. So if we just extend that and start adding different powers, right? All this is basically saying is x to some power, and then one less than that, until you get down to 2, 1, and 0, right? So that's a standard form of a polynomial function. It's in descending order, so your largest power comes first. So if this is the 5th power, then the 4th power should come next, so on and so forth. If you're missing a power, you just skip that power, right? The important part for us, for a polynomial function, is this part that's right here, that's why it's in bold, right? For a function to be considered polynomial, every exponent in there has to be a positive whole number. Obviously, you know what positive means, you know what a whole number means. What's a whole number? 1, 2, not a decimal or not a fraction, and not a square root, right? Not a radical. So positive whole numbers, some you can count by, some of you started counting 1, 2, 3, right? Positive whole numbers, right? I already talked about standard form. Standard form is important because it makes it easy to identify the leading term, right? So the leading term is the first term in standard form. And then it's important to know the leading term because the degree, which we'll hear this a lot throughout this unit, what's the degree of the polynomial? What's the degree of the polynomial? What does it tell you, right? So the degree is that largest exponent. So if I find the leading term, I know what the degree is because I can just look at the exponent in that leading term, okay? But it's the largest exponent. Not everything will always be given to you in standard form. Sometimes you have to rewrite it, okay? But the degree tells us a lot of information, and the leading term does tell us a little bit as well. The coefficient that's in that leading term tells us some information, which we'll see here in a little bit. And then the very last part, the constant term, is less important, all right? It's the term at the very end without an x in it, right? But it does tell you at least your y-intercept, just like it is for quadratic, ax squared plus bx plus c. The c told you the y-intercept. Same thing here. Whatever that constant is going to tell you the y-intercept of the graph when we start looking at graphs, okay? All right, so the first example is just taking that and saying, do I have a polynomial function? If so, write it in standard form. If not, why not? Okay, so you're looking at, does it meet the criteria? We said positive whole numbers and all of the exponents, right? So that first example, p of x is equal to 5x cubed minus 1/4 x squared minus 9. Are all of those exponents positive whole numbers? Yes, so this is a polynomial function, so you can say it is a polynomial. And then it says for each polynomial, identify the leading term, constant term, and the degree, and then write it in standard form. So when you write it in standard form, this one actually is already in standard form because I've got 5x cubed is the largest power, and then x squared. I'm missing an x term, but that's okay. We can be missing terms. So that's the standard form. The leading term is the entire 5x cubed. The constant term is the minus 9. Keep the sign with the term. And then I skipped this part, but it does say state the degree. So this is a polynomial. What is the degree of that polynomial? It's the biggest exponent you see. 3, so it's a polynomial degree 3. That's it. Just identifying, are you looking at a polynomial function? If so, identify these things. If not, why not? Okay. So then in B, is that a polynomial function? Exponents are positive whole numbers, right? So this is a polynomial. Again, what's the degree of this polynomial? Is 4. Right, so that's an example of one that's not in standard form, obviously. So I need to rewrite this one, and that x to the 4th term needs to come first, That negative is attached to the 3, so it's negative 3x to the 4th. And then I have a positive x, so plus x, and then a plus 2. So I'm missing a few terms there. I'm missing an x cubed term. I'm missing an x squared term. Right? And that's okay. Leading term is the negative 3x to the 4th. Constant term is a positive 2. Okay, and then we go to C. G of x is the square root of x. Is that polynomial? No, it's not. Why not? Why not? It's not a whole number. What is that exponent if you rewrote square root as an exponent? Do you remember from Algebra 1? If I rewrite square root as an exponent, it actually becomes a fraction, so it's the 1/2 power. Okay. So you could say either one of two ways. You could say it's not a polynomial function because it's a radical function, which is the next type of function we'll look at. Or you could say because the exponent is not a whole number. Those two justifications are the same thing. So it's not a polynomial, it's a radical function. Or you could say the exponent is not a whole number. Okay? And whether that's a standalone square root function or if that's just one term within it, right? So if that was something like just throwing in there the rest of it, if it failed, one term fails, the whole thing fails. Right? So every term has to meet the criteria, and that one doesn't. Okay? And then last one, D, x squared minus 2 divided by x cubed minus 1. Polynomial. Kind of looks like it because all those exponents are positive, but I would actually write this x cubed minus 1 is a negative 1 power. So polynomial functions by definition don't have fractions. Okay? So this is also not a polynomial. It's a rational function because it's a function that's got a variable in the denominator. Okay, so let's just identify degree, lead term, constant. And the reason you want to be able to identify those things when we start talking about behavior of polynomial functions, the leading term is going to tell you a lot of information. Right? So talking about in behavior of polynomial functions, and then there's this blank down here, some space for you to write. So if I said sketch the graph of x squared, that's one of the parent functions you're supposed to know. Right. It's just that parabola that opens up. And if I said sketch the graph of x cubed, it's the kind of squiggly line. Yeah. So it kind of starts down here, flattens out at the origin, and then keeps going. Okay. So if I know those two characteristics of those two, then I can take that and apply it to any polynomial, because as I start increasing the power, that behavior doesn't change, it just, the middle part changes. And all we care about is the end behavior. Okay? So if I said sketch a graph of x and then do any even power, if I just worry about the ends are going to end up going the same direction. You don't have enough information to say what's going to happen in here. You actually need to know what the power is. But if I know it's any even power, I know that those two ends are going to do the same thing as a quadratic graph would. They're going to go the same direction. Okay? And then same logic, if it's any odd power, or odd degree, I know this end's going to go down and this end's going to go up. I just don't have enough information to say what's going to go on in there. Okay. When does this end behavior change? So the graph of x squared, both ends go up. When is it opposite of that? So we said the degree is going to be important. Tell me what the behavior is. Well, what can change this graph? Flip it what? If it's negative, right? So the same thing, if I have a negative coefficient out front, whether it's -1 or negative anything, if there's a negative out front, then it takes that quadratic and flips it over. The same thing happens down here, right? It just, my end behaviors would go down. I don't know exactly what's going on in here, but I know both ends are going to go the same way, okay? And then negative x cubed does the same thing. Right? Okay, so the end behavior of the polynomial, that's what you're talking about, right? I'm trying to figure out if I just look at the polynomial function, if I just said, oh, well, I have this polynomial function, describe the end behavior. So the leading term is going to tell us everything we need to know. So if I said, well, this leading term is negative 3x to the 4th power, that should tell me enough about the end behavior, okay? If you had to guess, based on all of those things we just did, what would the end behavior, or which of these 4 things would that look like? Negative x squared? Why? Because the exponent's even, so we know the behavior is the same way, and then the coefficient's negative, so it's going to go down instead of going up. Okay, congratulations, you know everything you know about end behavior. So on the back, basically one of those 4 things is going to happen for any polynomial function. So your behavior goes up together, or goes down together, if it's even, or your behavior goes opposite, right side up, or right side down, depending on if it's odd. Okay. For me, I always look at figure out the right side first, because the right side, right? This coefficient here is positive. What's the right side doing? It's going up. Coefficient's positive, right side. It's going up. Coefficient's negative, right side. It's going down. Coefficient's negative, right side. It's going down. So if you just tie the right side of it to the coefficient and then know if the left side is supposed to be the same or opposite, but even or odd, then you can do end behavior really, really quickly. Like free questions on quizzes and tests. Okay? Out of that. Cool. Says, so the end behavior, the limits at infinity of a polynomial function depend on what 2 things you just told me? And the exponent, so we're going to use the word for that, the degree of the polynomial, right? Tells me, right, I need to know, is the degree even or is it odd? Right, because if I know the degree is even, I know the behaviors do the same thing. If I know the degree is odd, the behaviors are opposite. And then specifically the leading coefficient tells me up or down, right? So I need to know if that leading coefficient is positive or negative. I don't really care about how big or how small it is. I just know, is it overall, is it positive or negative? And then we haven't used the limit statements in a while, so I'm going to put the general limit statements you're going to use up here, right? So remember that was the limit as x is going to negative infinity. So we did these when we did the horizontal asymptotes before in the first quarter, right? Of the function, whatever the function's called, usually it's going to be f of x, but not always. And then you're going to put an answer there after the equal sign. Okay. So that's the limit as x goes to negative infinity, and then I need a right side and a left side. So negative infinity is the left because x is going to the left. And then so I need my right end would be x goes to positive infinity. The good thing for you for polynomial functions is you have only 4 possible answers. Right? Really, you only have 2 answers per blank, right? It's either positive infinity or negative infinity for any polynomial function. It's never going to flatten out. They're always going to go to infinity or negative infinity. And you have. So, on the example, describe the end behavior using limits. So you want to identify, do you have a polynomial function first? So x cubed plus 2x squared minus 11x, that's polynomial. I only really care about this leading term. Just make sure it's not just the first term. Make sure it's the largest power. Right? What's the degree? 3. So that's odd. So this is kind of the thought process you would go through, right? It's odd. So now my behavior is going to be opposite. And then the coefficient, is it positive or negative? Positive. So I have an odd positive. Right? So then I am going to have my limits, right? So limit as x goes to negative infinity of this function, and then the limit as x goes to positive infinity of this function. Again, I always do the positive infinity one first, because I know it's going to follow the coefficient. So if the coefficient is positive, the right side goes to positive infinity, and then I go back into the left side. The left side is, because it's odd, it's opposite, so the left side would go to negative infinity. And that is your 2 limit statements. Right? And so no matter how many terms a polynomial has, because you could have a bunch, obviously, all you really care about for end behavior is the degree, so the leading term. So x to the 4th, x cubed, x squared. So this x to the 4th is the largest term, or is the degree. That one's now even, so both ends go the same direction. The coefficient's positive. So I know before I even write the whole limit statement, I know both answers to this are going to be, both are going to go up. Both are going to go positive infinity. So then you just have to take the time to write the limit statement. So limit as x goes to negative infinity goes up. The limit as x goes to positive infinity goes up to positive infinity. It would be that situation if we're sketching a graph. So if you're finding the zeros of a function algebraically, right? Right now we just want to factor it. Make sure we're doing that part right. So we said take a GCF out. So there's a common factor of an x in this first one. So if I take the x out of that, that leaves me with x squared minus x minus 6. Okay, that x counts as a factor. And then you need to factor what's left in there, which most of you are doing the x puzzle. So I need factors of negative 6 that combine to be negative 1. So 2 and negative 3. And then that means my factors, because a is 1, I can just write these as 2 factors, x plus 2 and x minus 3. Okay, so that is the factored form of that. And then if we're finding the zeros, that means I have zeros at x equals 0, x equals negative 2, and x equals positive 3. So I should have 3 zeros, not just 2, because that GCF that you took out has an x in it. So now I can set it equal to 0, and that means x equals 0 is also a 0. So kind of like with quadratics, when it was x to the second power, you were expecting to have 2 answers. If it's x to the third power, you're expecting to have 3 answers. Okay, so it's another thing the degree can tell you. The degree can tell you how many answers should I end up having usually. All right? So same thing happens on B. This has an x in common, so I can take the x out. That gives me x squared minus 49. Again, you could factor that using the same x method, but this is just x squared minus 7 squared. So that's the difference of 2 squares. So I could factor it, and that's x plus 7 and x minus 7. And so then my zeros are x equals 0, x equals negative 7, and x equals positive 7. Okay, and then we get to C and D, and now I have more than 3 terms, which we haven't dealt with a lot. But because I left the little note on there, you kind of know factor by grouping. So if I group these two things into 2 terms with 2 terms, right, what ends up happening is there's no GCF across the whole thing, but there is a GCF in this first group. What's in common in these first 2 terms? There's an x squared I could take out. So if I take the x squared out of that, what's left? X minus 6. And then there's a common factor with 4 and 24. There's a 4, so I can take a 4 out of that. And it's a positive 4, so I'm going to put a plus 4 right there. And if I take that out of there, what's left? So, and then that now is a common factor. So that I can take it out together. Both of those terms on opposite sides of that plus sign in the middle, both of them have an x minus 6 in it, so it's a common factor. So I can take an x minus 6 out of that, and then I have an x squared plus 4 is left. So that's my function in its factored form, which means I have a 0 at x equals 6. Does x squared plus 4 ever equal 0? Can you factor it? Kind of. It's x squared and 2 squared, so can you factor it? No, because it needs to be minus, not plus, right? So we can't factor it. How else could you solve x squared plus 4 equals 0? We just did a quadratics test that hopefully you could answer a question like that. Subtract 4, so the extracting roots method. So you get actually would have the other 2 roots would be imaginary, right? Okay. And then for D, same thing. The only difference is now there's a minus sign in between here, so I want that to be a plus sign in between. So if you have a minus sign in between, I'm going to change this to plus a negative so that I can attach the negative to the 21 and be left with a plus sign in between here, because otherwise this factoring by grouping method doesn't work. Your signs will be messed up. Right. Take out the GCF from each. What's the GCF of 24r cubed and minus 64r squared? 8r squared. If I take 8r squared out of that, I'm left with, what, 3r minus 8? And the GCF of negative 21r plus 56? 7. But I do want this to end up being a positive 3r, so I'm going to take the negative out with it. So I'm going to take a negative 7 out, so that I can force that lead term to be positive again. So minus 7 comes out. 21 divided by 7 would be 3r. 56 divided by negative 7 would be minus 8. We get what we want to have that repeated factor. So my factors would be 3r minus 8 and 8r squared minus 7. And if I'm finding the zeros of that, I know I have a 0 at r equals 8/3. That's a linear factor, so that one's easy to find. And then how would I find this one? Same thing as the other one, it's just a little bit messier, right? So I would just say 8r squared minus 7 equals 0, which means 8r squared equals 7, which means r squared equals 7 over 8, which means r equals plus or minus the square root of 7/8. And you can leave it like that. So if you get down to something that can't factor, a quadratic that can't factor, you have a bunch of ways to solve it. All right? You have a quadratic formula, complete the square, or in this case, these last two haven't had a bx term in it, so just get the r squared part by itself, take the square root of both sides. All right? multiplicity of zeros, okay, if you can get a function to its factored form, right? So we have a polynomial in standard form, right? If you write the polynomial in its factored form, just like you did with a quadratic in its factored form, right? So on and so forth, right? So depending on how many times you cross the x-axis, you would have a factor for each one of those, okay? So what the multiplicity is talking about, right, is if a polynomial function has x minus c to the n power as a factor, okay, then c is the 0, which is what we talked about. Right, so I wrote it as an r, but you can use a c. And then the multiplicity is the power that's on that exponent. So essentially, if you have the factor being repeated, however many times that factor gets repeated, which we shorthand that with an exponent, right? So like this x to the x minus 3 to the third power just means that factor is there 3 times. So instead of writing it out 3 times, we just say it's counting 3 times. Okay, that's called the multiplicity. And the multiplicity of the 0 is going to tell us some behavior in the last part where we start sketching graphs. Okay, so it says find the zeros and state the multiplicity. So this function is already in its factored form. So if the factor is x minus 3, the 0 is x equals 3. The multiplicity of that 0 is the power that's on it, which is a 3. Okay, if the factor is x plus 2, the 0 is negative 2. The multiplicity is the power that's on that factor, which is a 2. If there's not a power there, its multiplicity is 1, which will be the most common. Okay? Versus graphing polynomial functions. It says if a polynomial function has a real 0 of odd multiplicity, then the graph will cross the x-axis. All right, so what that means is if I have a 0 at whatever that value is, right, x equals c, and I know the multiplicity is odd, so for a multiplicity of 1, it's going to cross through kind of like, if you were to zoom in on the graph, it would look like a linear function. It would just cross straight through, all right, x to the first power. As that multiplicity increases, right, so if it goes to, multiplicity is 3, so still odd. We're still going to cross through, but now it's going to look kind of like an x cubed graph. It's going to flatten out a little bit and then continue going the way it was going, all right, whether you go from increasing or you could be decreasing. And again, as that power increases, right, to the 5th power, I'm just going to be the last one because you kind of get the idea at that point, right? It just flattens more. So the higher the power, the more it kind of flattens out, and then it's going to keep going the direction it came from. Okay. If it's even multiplicity, then it's going to just touch the x-axis, and I want you to get used to using the word tangent. Okay. So if I say the graph is tangent to the x-axis, that means it's just touching and going back the way it came from, right? So this is the vertex on the axis from a quadratic. So if the 0 has a multiplicity that's 2, it's going to approach the 0, touch, and go back the way it came from. So it's going to look like a parabola with the vertex on the axis. All right. If I'm multiplicity of 4, same thing. It's just going to look flatter at the bottom. Okay. So on and so forth. Okay. Rarely will you have to go beyond to the 5th power, because sketching that gets hard. You can't really tell visually what's the power, how flat is it. So typically you just need to know up through the fifth degree. So I'm going to identify each of these zeros and then their multiplicities, right? So if x plus 2 to the 3rd power, that means I have a 0 at x equals negative 2. The multiplicity of that is 3, because it's to the 3rd power. And now I can add the piece, well, if the multiplicity is odd, then I'm going to cross the x-axis at that 0. So at x equals -2, when I go to sketch the graph, I'm going to cross through the x-axis, and I know it's going to flatten out because the multiplicity is 3. Okay? And then I have x minus 1 squared, so that means my other 0 is going to be at x equals 1. It's squared, so the multiplicity is 2. And because the multiplicity is even, it's going to just be tangent, or touch the x-axis. Okay, so if I'm going to sketch this graph, and we'll come back and get the degree in a minute, right? I can at least put the zeros in the right places because I'm not guessing where they're at. So I'm going to scale the x-axis. I'm not going to really worry about scaling the y-axis right now. Okay, so I'm going to go to -2 on the x-axis. And know I have a 0 there. And I'm going to go to +1. And I have a 0 there. Okay, so I know at -2, I'm going to cross through the axis. And at +1, I'm going to just touch and go back the way I came from. I need to know what the end behavior is. So I need to know, does this right side go up or down? How do you figure that out? I need the standard form, sort of. Do I need the entire standard form? I just need the leading term, right? So I just need to know what is x cubed times x squared. X to the 5th. So this is a degree 5. So I know the behaviors are opposite. One side goes up, one side goes down. This leading term right here was a equals 1. It's positive. So even if I didn't multiply it all the way out, I could get the leading term pieces that I need to know by just add your multiplicities together. So 3 plus 2 gives you the degree. It's the kind of shortcut way. You don't have to multiply it all the way out. Right? So just do 3 plus 2 is 5. That's the degree. And then look at the term in the front. If it's a positive there, then we know the right side is going up. So I know that this right side should go up now, which means the left side, because it's an odd degree, is going to go down. So now I just need to get from my starting point over here. So I'm going to go left to right. So I'm going to start from here. I'm going to go through this 0, right? At -2, I'm crossing through the axis and flattening out a little bit. So I'm going to approach that 0, flatten out a little bit, and continue going the way I came from. Right, so crossing through. At some point, right, I've got to get from here to this next 0. Again, we're not really scaling the y-axis, so it doesn't really matter how far up you go. You need calculus to be able to figure out where exactly that's at. You're not there yet, obviously. So we're going to round it off and come back down the way we came from, right? And then at this next 0, I'm supposed to be tangent, so bounce and go back the way I came from, which is good because it takes me to the end behavior that I'm trying to get to. Okay? So there is its crossing, and there's where it's tangent. You don't have to label that on your actual graph, but that's what it's talking about in the words before.